Welcome, 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 everyone. Happy Thursday. Today, we're going to be talking about angles, angles, angles. And this is webinar 4 in our series. And I'm Janelle Mills, the high school math ed associate for education and standards.
Bye. Have a
We
nice
have Lorraine Jackman, who is the secondary ed associate, and Dawn Hood, who is our middle school education associate.
Hi, y'all.
I hope everyone's been having a great week. I know some of you are testing, so not much time left in school. Well, again, I want to welcome you and thank you for all that you do for the students here in South Carolina every day. As a disclaimer on the use of AI, the content presented is the intellectual property of the South Carolina Department of Education. By participating in this event, attendees agree they will not record, capture, or share its contents without permission. Attendees agree they will not use artificial intelligence to capture or summarize the contents of the event. The SCDE reserves the right to remove attendees using these services. Your recertification credit today is based on your live attendance and participation, that you remain in attendance for the duration of the presentation, and at the end of this, you will complete attendance and the feedback form. So we are happy to announce that we are offering 1 hour of recertification credit for webinar participation. And of course, I just read you those 3 requirements. So our purpose for today is to train, equip, and to demonstrate.
Usage and all of that with that as well.
So looking at our purpose today, we have a quote. Geometry enlightens the intellect and sets one's mind right. All of its proofs are very clear and orderly. It is hardly possible for errors to enter into geometrical reasoning because it is well arranged and orderly. Thus, the mind that constantly applies itself to geometry is not likely to fall into error. In this convenient way, the person who knows geometry acquires intelligence. I want you to take a minute to think about how this connects to the work we're going to be doing in this webinar. Now, the focus is to demonstrate strategies to introduce the HQIM resources to teachers and encourage using these materials to provide instruction to students. During these sessions, content will be discussed because this may be the first time teachers has taught geometry or statistics, and while some may be comfortable with the content, others may need more support. So what about this quote today kind of resonates with you? You can unmute or you can put your response in the chat. Proofs develop reasoning. Okay. So today again, orderly and logical. Yes, geometry has a lot of order and logic. Many students and teachers feel that geometry is abstract, but this quote describes it as orderly. Yes. I think this is a great way of developing mathematical minds, promote that way of thinking in all we teach. Yes, thank you. Proofs help develop logical, critical thinking. Great way of explaining our steps algebraically or getting conceptual understanding. Yes. So geometry, if you notice, geometry is all around us every day, and we see it,
You did.
we apply it, and sometimes we need to
Lo que
not
tiene
have
es-
students
Ujú.
think that it's such an
Anina,
abstract
cero.
concept. Algebraic concepts can be backed up by geometrical concepts. Okay, great. Proofs help students order their thinking similarly to how geometry itself is orderly. Very good, yes. So today we're going to take this and we are going to focus on standard GS MGSR 5 and indicator GS MGSR 5.1. So let's talk about today's standard and indicators. And when you read this standard and indicator, what resonates with you? What keywords tell you what students should be able to do after learning this indicator? So our standard is to demonstrate whether a conjecture or theorem is true or false using a variety of algebraic and geometric explanations. And our indicator is for students to justify and apply the attributes of angle relationships or lines in mathematical and real-world situations. So when you read this standard and indicator, what resonates with you? Demonstrate, okay. Demonstrate with explanations. Okay, good. Apply, yes. Content vocabulary will be essential to communicate efficiency. All right, variety, yes. Now, as we talk today, justifying your thoughts, exactly. So students are going to be demonstrating and they're going to be justifying and applying. So we have a DOK, justify at least at a level 2 question, right? So we're already starting at a depth of knowledge 2 and moving above. Now, as we're talking about this, and I'm going to stress, in the standard, it says we're using a variety of algebraic and geometric explanations. Now, when we started this journey with having geometry with statistics come before algebra, and there were a lot of questions and concerns about students not having enough algebra to do the geometry, I want to make it clear that even though we're moving toward teaching geometry in a more conceptual way, it doesn't mean that they won't do any algebra. So let's not think about it as because we're talking about geometry, there'll be no algebra at all. They do go hand in hand in some instances, and we'll talk about that a little bit today. And the main focus of this is to give you some instructional strategies and to provide some support for teachers that may have never taught this geometry before, taught geometry at all before. And so that's what these webinars are kind of based on. We're not digging deep into a standard, and it's not my place to tell you how to teach it, because everyone has their own style, but the content itself is what we're focusing on. Okay, we have a response in the chat. Basic solving is before Algebra 1. Yes, it is. And though it's algebra in this a simpler form, it's still an algebraic explanation. All right, let's look at our indicator insights. So we have a lot of insights in 5.1. So we're going to start with this first one. So looking at this first indicator insight, how will this help you make sure students can master the indicator? What do you notice about this insight? Algebra and geometry go side by side. Yes, it can. And so this insight talks about proofs of theorems can sometimes be made with transformations, coordinates, or algebra. All approaches can be useful, And in some cases, one may provide a more accessible or understandable argument than another. So we have the concrete and the abstract going hand in hand. As this insight states, they can sometimes be made using transformation coordinates or, and there's or, algebra. And it's saying all approaches can be useful, and in some cases, one may provide more accessible or understandable arguments than another. So sometimes the algebra is the better way to prove a theorem, sometimes not. So we have some comments in the chat. We have transformations, coordinates, and algebra are all 8th grade standard. Yes. So this is not brand new to students. It's reinforcing and it's building upon indicators they've already covered. For so long, we use 2-column proofs. We're shifting to other approaches. Yes. And that's another point to be made. We are moving away from formal proofs. Now, we're going to talk about today how you can actually have a proof without that 2-column structure. All right, so let's look at our next set of indicators, insights. So our second part of the indicator insights has that we're going to apply in mathematical and real world context, that vertical angles are congruent. When a transversal crosses parallel lines, alternate interior angles are congruent. Alternate exterior angles are congruent and consecutive. Interior angles are supplementary. Any point on a perpendicular bisector of a line segment is equidistant from the endpoints of the segment. Perpendicular lines form 4 right angles. Base angles of isosceles triangles are congruent. Oh, thought I had one more. So this is the second part of the indicator insights. When focusing on real world context, how would these move students toward mastery? Where would students see these indicator insights in a real world context? Streets, yes. We do have streets. We have carpentry, exactly. And if students need real world examples, I don't know, and you can raise your hand in the chat if you'd like to on your screen. How many of you have been to Aiken and Charleston where you have lots of one-way streets and you have lots of parallel roads, and most downtown areas have parallel and intersecting roads, right? Railroads, yes, railroads, surveying. So these are all examples. If students say, well, when will I ever use this? Or when will I ever see this? These are all examples. Or you can say, hey, you'll be able to see it here. I lived in Aiken for a brief minute, but those roads, I was like, oh no, parallel streets everywhere. Pickleball court, okay. So our third insight asks us to define angle, perpendicular line, parallel lines, line segments, raised circle, and skew in terms of the undefined notions of point, lines, and planes. So this third insight, how will it help you make sure students can master the indicators? You can unmute or you can put your answer in the chat. Apply the definition, yes. That goes back to our indicators where we're justifying and applying. But when students have this accountable talk, exactly. Students should be using mathematical language in the classroom, yes. It helps build on prior knowledge of points, lines, and planes, exactly. And it helps reinforce what they're learning. So when they see these words, these terms on assessments, they'll know the proper language and they will be able to answer the questions. If they don't know what parallel lines are, they wouldn't be able to justify their proof. And we're going to talk about that as we move on. Very good. So on our agenda today, we are looking at a little closer to MGSR 5.1. And as we talked about before, when we have our mathematical process standards, even though there's only one listed here, we know that we'll use more than one mathematical process standard as we move through our standard and our indicators and our indicator insights. So I have a little activity for you to try. Now I'm going to give you a minute of think time, quiet think time. Then I'm going to give you 1 minute to respond. I want you to look at this diagram. And I want you to think about, what do you notice and what do you wonder about it? So you can put some of your what do you notices and what do you wonders in the chat. We're going to start with what do you notice. And don't put it in quite yet. Give yourself a little time to think. And then I'll let you know, and you can type it in, and I'll let you know when to submit. What do you notice about this diagram? Okay, we have a lot of notices. So let's see. Go ahead and submit your notice, or you could come off and mute and tell us what you noticed. So in the chat, we have circles with the same centers. Okay. We notice the circles have the same radius. We have 6 circles overlap in the center circle. I know how to make this one with the compass. Great. Geometric flower. Oh, okay. Yeah, we have a flower in the middle. Congruent circles. Design made up with all circles, but creates a new design, more like a flower. Okay, great. Circles that have been transformed. Overlapping points. They all connect in the center of the circle. Okay, we have some repeat overlapping points. Circles are congruent. If the points connect, it makes a regular hexagon. Yes. Very good. All right. Now, what do you wonder? So what about this diagram do you wonder? You had some great observations. What do you notice? Is the same circle rotated? That's a good question. Venn diagram. Okay. How many circles are there? All right. Which circle was drawn first? Great question. Are the circles translated or reflected? Okay. What's another question? Those are our great wonders. Rotational symmetry. Good. What else do you wonder? Those are a lot of great wonderings. Now we go back to what we noticed. What angles can be formed? What is the area of each section of the circle? I started wondering about finding the arc length and sector length, number of circles, and the congruency among the circles. Very good. Those are great questions. Those are great wonderings. If we continue the pattern out, what would it look like? Excellent. Yes, those are excellent wonderings. Now, as you're talking about this in your classroom and you're presenting a diagram like this with your students, and you're giving them the opportunity to talk about what do you notice and what do you wonder, they're going to be having these same conversations and collaboration with their classmates. And you can do think, pair, share. You can do full class responses. But the idea is it has a low floor because all students can answer these questions. There's something that they notice and something that they wonder. And then as they're working through this, it kind of elevates their thinking like, oh, I didn't think about that. When we talk about congruent circles, how do we know the circles are congruent? Have we measured anything yet? We talk about symmetry. We talked about sectors, sector lengths. It's a great inquiry lesson. And so this gives students the opportunity to explore these concepts. All right, now, when students attempt this problem, they will only have angle KWT to start. Now, this is an activity, and I pulled this from Accelerate Learning Math Nation. And so it gives them this angle, and it tells them that point P lies in the interior of angle KWT as shown. So now just looking at this diagram and the explanation that point P lies in the interior of angle KWT as shown, what should students be able to deduce from just this information if they don't know what interior and exterior is yet? P is not on either ray. Very good. Okay. Should they understand now what interior and exterior are when we're talking about angles? Yeah, they will be able to tell that P is on the inside of the angle. Very good. So we have another set of directions that ask us to draw ray WP. So now they've drawn this ray. So now they understand what a ray is. So now they understand what a ray, and they've drawn this ray. Then we want students to measure each of the angles. Yeah, the angle ray goes on forever. So that ray should have an angle at the a little triangle at the end of it. And once they draw this line segment, we give them a question and say, okay, let's say angle KWT is 70 degrees. And the measure of angle KWP is 44 degrees. Then when students measure angle PWT, what measure should they get? So as we move on to the next section, and we ask students to use a protractor to measure each angle in degrees. So they measure the big angle and they get 70 degrees. Then they measure KWP and they have 44 degrees. When they measure angle PWT, what angle measure should they get as an answer? Right, they should get 26 degrees. So let me ask you this question. What can students conclude once they have completed measuring each angle? Ah, the sum of two smaller angles. Yes. The sum of the angles adds equal the large angle. Yes, the angle addition postulate actually works. So would we just give students one of these angles to measure? we would give them multiple examples, allow them to measure them, and they're going to conclude that if we measure these smaller angles, they're going to add up to equal the measurement of the larger angle. And because they've done this more than one time, they're going to conclude that this is the case every time. And they have just proved the angle addition. Now, as you're talking about this with your students, you're like, okay, so we just talked about this, and I'm giving you examples of how this is true. Students are going to come up with this, and they're going to say, wow, I really learned something today, because now I know that when I add the measure of the two smaller angles, I will get the measure of the larger angles. And it should be true each time. And not only did you do the math behind it, we gave them sort of an equation without an equation. So there are no variables where they're solving for a particular variable, which is the abstract part. This is more of our concrete, where they're actually doing it for themselves. You could also have students draw angles, give it to a partner to solve, and that moves us into representational. And you can do this either using Desmos or GeoGebra. And then you move on to the abstract. Okay, we have a state. This is verification, not a proof. Well, it isn't a way of proof, because when we start talking about it and we say, okay, the measure of angle KWT is 70 degrees, that's a statement. How do we know that? That was a given. I gave that to you. That was automatic. Or you could have measured it, and that still would have represented a given. Then you have the measure of angle KWP is 44 degrees. That was something that you measured. When you found the measure of angle PWT, whether by subtraction or you measured it again, once you say, okay, when I added the measure of angle KWP and I measure the angle of PWT, and the sum of those two angles is equal to the measurement of angle KWT, then we just concluded that this should be the case each time. Now, once you do this enough times, then that's actually creating a proof, because that's all proofs are. You have a statement, and then you have the reason that it makes that statement true. Right. And so once we do this enough times, you're giving the students logical reasoning. By logic, that should work every time. And we're going to talk a little bit more about that. Every proof doesn't have to be complicated. So now, with all the information that we've given students and this discussion that we've talked about, and a lot of us are used to seeing it in a two-column proof or a flow chart or a paragraph. So this is going to be an adjustment. It's not that they're doing anything different. It's just, instead of it being in a formal format, we're discussing, we're collaborating, we're talking about it. And whether they write it down and they prove it, it's still a justification. And at the end of the day, that is what proofs were or are. Yes.
Okay, so the angle addition's a postulate. So the postulates we don't actually prove. Do we at this point like talk to the kids that this is something that we accept without proof? So given that we've looked at multiple things, because I'll tell my students the difference between postulates and theorems. And so with this one, it's actually a postulate, right? Or
Right.
I might be just getting confused. So do we still introduce the differences between the postulates and the theorems?
You want to, okay, so, and I want to phrase this correctly. We want them to explore it. it's more of an exploration. So you wouldn't really be introducing this is this postulate or this is this theorem. As they're exploring this and they're measuring these angles and they're coming up with their conclusion and their deductions, then they're really proving, because that's all our postulates and our theorems are. This is a rule that happens all the time, no matter what. Now, granted, we have exceptions to those rules, but this is something, a rule that happens. So when they add up these, the reason why we came up with the angle addition postulate is because whenever we add two angles, two smaller angles, they are the sum of those angles equal the larger angle. That's not going to change. So instead of us telling them this, they are discovering this. And so that's helping them to understand the basis of it. Like, how did this postulate even come to be? Well, that's because somebody was out here measuring some angles and they said, oh, if we do measure this angle and this other angle, and they have a common side, adjacent part, then that sum is the larger angle. And if it's not making sense, please let me know. But that's the whole point of the geometry with statistics. There are not that many indicators. There are less indicators than there are days in a 9 weeks. I think geometry with statistics has maybe 33 indicators. So it's not a rush to get this done, get this done, get this done. It's allowing you to have time with the students to have these discussions, to let them explore without you giving them something. And then they'll be able to have a deeper understanding. So then by the time we get to the question, our next question on here, which is, okay, if we know the measure of angle KWT is equal to 70 degrees, and then we have the measure of angle KWP is 5x plus 5 degrees, and the measure of angle PWT is equal to 4x minus 7 degrees. Now we want them to determine the value of x. Well, at this point, it's not, oh, I don't know where anything goes. They've already talked about an interior point. They already have their interior angles. Now, when it comes time to have an abstract take on this, they don't have to guess at, well, where does the 5x plus 5 really go? And what is 4x minus 7? They already understand the structure. Now we can get into the algebra, and it is nothing they have not already done, because all they're going to do is add 5x plus 5 plus 4x minus 7 and set it equal to 70 degrees. They understand about combining like terms by now. They've already done that in middle school. They've already solved simple equations, multi-step equations. They've done that in middle school, in elementary school. So now, when solving for x, it shouldn't be a larger task. Any questions? So out of curiosity, in the chat, what would x equal? Very good. Now, David, when we have these students do this, what are we gonna have them put? Are we gonna just have them put that number down there? Ah, that's right, Chastity. We're going to have them show the work, and we're going to have them they're going to have to say x is equal, the value of x is equal to 8. And this is a conversation you can have when we start talking about equivalent and congruent and equal, because there's a difference between congruency and equality. Those are conversations that can come up and come about. So you did have a question. whether or not to have this class as a year-long or a semester course is a total local decision. And you can look at it both ways. What I'm saying is that because it is not a rush and because some of these indicators can be combined, it really gives students a time to get a solid grasp on the math. And so when they move on to Algebra 1 should not be such a hard instructional teach. Students should be coming to you with solid knowledge and they should remember it because they've had time to have it. They've explored it. They've discovered some things they may not have known about math. And now they're actually able to understand the math from the bottom up. Yes, that's exactly what the equation will look like. All right, let's look at another one. This is what's true, and it's from Accelerate Learning. So what is true about this figure and how do you know? So we have plane P is shown containing line NH and line SG. Question is that we want students to select all of the statements that are true and express how they know that the statement is true. So looking at this, what's the first statement? We have our statements line NH and SG are perpendicular lines. Lines NH and SG are parallel lines. Angle GYS is a straight angle. Angle NYS is a straight angle. Point P is on the plane. Point H is on plane P. All right, let's talk about this. We see, okay, we've got the lines are perpendicular. The lines are perpendicular. How do we know that the lines are perpendicular though? You can't just say it. Ah, okay. The first one is true because they form a right angle. They meet at 90 degrees. How do we know that it's 90 degrees? Ah, because of the symbol, right? That small square. That lets us know that it's 90 degrees. All right, so we know that it has one 90-degree angle, but just because it's one 90-degree angle, how do we know that all of the angles are 90 degrees? All right. So how do we know that angle GYN is 90-degree angle? Ah, okay. So we know that lines NH and SG are perpendicular lines. They intersect. Do they just intersect or do they bisect? All right, we have some opposing views in the chat. Okay, we have some intersect and we have some bisect. What's the difference?
The number minimizing.
You cannot bisect a line. Ah, why can't you bisect a line? This is a conversation you would have with your students. It needs endpoints because what's the definition of to bisect something? Ah, there we go. Two equal parts. To bisect is we don't have right to divide in half. And a line is infinite. So that's not possible. So when we're talking about this, there's a difference between to bisect and to intersect. So two lines can intersect at any point, right? All right, so they intersect to form how many right angles? Good, 4. We have 4 right angles. And that's what makes we have perpendicular lines. All right, so we know the lines aren't parallel because they are perpendicular. But what else do we know? Is angle GYS a straight angle? Yes. And we know it's a straight angle because how? Ah, they're made up of two right angles, and the sum of those angles is equal to 180 degrees. Exactly. So we know that that is true. All right. How about angle NYS? Is that a right angle? Yes, we've already measured that. We've already talked about it. It's a part of a straight angle. We know that. Good. What about point P? Is point P on the plane? Ah, there is no point P, right? Point P does not exist. P names the plane exactly. So now in discussing this one diagram and with these 6 statements, what did we just cover? Or what did the students just discover in this whole conversation and talking about this diagram? We discussed what are perpendicular lines exactly, and not only what they are, but how they came to be. Definitions and terms, yes, lots of vocabulary. We talked about some other things too. Lines, angles, and planes. Yes, how a straight angle looks, exactly. The difference with parallel and perpendicular lines, linear pairs, supplementary angles, congruent angles, and vertical angles. We talked about not being able to bisect a line, perpendicular lines, symbols for points and supplements. Yes. Can you say that if you were to have this discussion just like this in class with your students, they would come away with a lot more information and a better understanding than what they came into class with? Yes. And it's good to have these type of conversations among us because I understand some of you might be like, oh, this is too simple. I don't need to know this content. But not just that. We had a discussion today between bisect and intersect, which you may not have even thought about before we talked about it. And so when you think about it, even though this may seem like, oh, we should know this, when your students come into class and they're coming in as fresh ninth graders right out of middle school, some of them may not understand some of this, and they need to have these more elementary conversations to kind of elevate them to the next level of thinking. All right, let's look at another problem. This problem is from Accelerate Learning. And we've talked about this before in middle school. You have line HL is parallel to line RG, line CV and line KD are transversals. The measure of angle KBM is equal to 117 degrees, and the measure of angle VTS is equal to 134 degrees. We want to determine the measurement of each angle. All right, so I'm gonna give you about a minute because it should be real simple for you all. What is the measure of angle DSG in this figure? And I'm gonna highlight it because it's not just you. This is your S. It looks like a backwards 3, and this is your G. So in the chat, what is your measure of angle DSG? $63 degrees. Very good. All right, so we have 63 degrees. Then we're looking at the measure of angle LMC. So the measure of angle LMC is 46 degrees. Then we have the measure of RTV is 46 degrees. And we have the measure of angle BWM as 71 degrees. But that's a great point. So even if you're teaching this in your classroom, and like I said, this is an example taken straight from Accelerate Learning. Whether you have students do this on whiteboards or, I don't know, some teachers get creative on their desk and you have the dry erase where students can write on their desk, and have students kind of share out in class or do think pair shares or couple students up. This is a way where we can talk about, okay, how did you get that response? This is the time when you can kind of clear up some misconceptions that students need and to see which students need the most support without giving a formal assessment. And then you can have these conversations in class so they don't continue with the same misconception. Now, looking at this and looking at the diagram, what do you notice? You can take yourself off mute, or you can put your answer in the chat. But what do you notice about this? Angle relationships, good. So which angles are equal? Ah, good. The alternate exterior angles. Right. So we have our alternate exterior angles that are the same. So if students don't know exactly what alternate and exterior are, now is that time to have that conversation. And honestly, if students wanted to, there are several ways that you could teach this concept. You could have them draw their own parallel lines and transversals and use a protractor to measure them and have them measure each angle, each set of angles, and then come up with a conclusion before you even enter into any mathematical addition, subtraction, and then they can conclude or deduce their way into that thought. Or you could have them do this, some similar problem where they already understand that a straight angle is 180 degrees, because we already had that discussion. And then they can talk about, okay, well, I know that 180 minus 46 will give me angle LMW's measure or angle CMH. Yeah, the 71 degrees would trip them up a little bit, but that's an extension. That could be considered an extension to ask them to find that angle measure. And then that's a discussion you can have. You can ask them, okay, if angle DSG is 63 degrees, what other angle would have the same measure? And you ask them, how do you know this? Let's look at this next. So we have relationships and triangles. And we have two triangles right here. And we have, this comes from Salvis and Vision. And the question is posed, well, if angle XWY is congruent to angle ZWY and XY is equal to 4, what is YZ? Now, how would you use conceptual instruction or concrete instruction to introduce relationships in triangles? What are some ways students could learn this concept hands-on before dealing with the abstract or representational? So if you have a figure like this, what would be the first thing you might have asked students to do? Measure with the ruler. Good, measure. Yes. So all those tools that we've had in the classroom over the years we don't take out and use very often, now is the time. So we're going to pull out those rulers or the protractors with the ruler attached to them, and we're going to measure. And so students would understand, well, if XY is 4, then ZY should also be what? 4, right. And if XY is equal to ZY, and the measure of angle ZWY is equal to 18, what is the measure of angle XWZ? Well, this takes us back to the concept we were just talking about before, right? And that's what concept did we start with today? Good, Jackie. So the measure of angle XWZ is going to be 36. And we know that because we talked about the angle addition. Exactly. Instead of it just being angles, now we have triangles. But the concept doesn't change. It's still the same rule. Right. And we know they're congruent triangles as we move into indicator. Now, this does move into indicator 5.2, but we know with congruent triangles that congruent parts make up congruent triangles. So now we know that they both have 90 degrees. We know that XY is congruent to YZ. We know that WX and WZ are congruent. And we know that angle XWY is 18 degrees and angle YWZ is 18 degrees. So congruent parts of congruent triangles are congruent. Yes. Well, Sandy, this is a good time for students to create their own. Or maybe you create some problems to give them so they have an opportunity to measure them. Because a lot of times pictures aren't drawn to scale in the books. But there's nothing to say that with some planning, you can't already have that in place for students. So they'll be able to see it before they move into the representational or create their own, and then move into the abstract where you introduce variables and the algebra. Pictures can. But that's when they have to rely on the information. And they should be able to see it's not drawn to scale. Right, so we're moving from the concrete to the abstract. So when we look at this, what would that look like during instruction? So with your concept, we have proving points equidistant. So the concrete or conceptual understanding is, well, we're proving these points at equidistance. That's when we have a line segment and we actually are measuring to prove the point is equidistant. You can relate theorems and graphs, and you can understand in the location of concurrent points. So when proving points, students investigate and then prove that the set of all points equidistant from the endpoints of a segment create a perpendicular bisector of the segments, and that the set of all points equidistant from the rays of an angle is an angle bisector. So that's when you're talking about bisectors, and that's the difference between an intersection and a bisection of something. Now, what does it look like in procedural skill and fluency? Well, that same concept, concrete concept, you would be constructing geometric figures. So if you're proving points of equidistance, you're going to be constructing those geometric figures in order to prove that those points are equidistant. Graphing circumscribed and inscribed circles. When it comes to locating points of concurrency, and understanding the point, the location of the point of concurrency is where they are understanding the actual point where it is located. Locating those points is using that information to do a representational part of that. That goes to determining valid triangles. And we talk about valid triangles. What if you had a triangle and they gave you the lengths of 3 sides? You want to determine, is that possible? Can that make a triangle? And we all know there's a algorithm that goes with that, but instead of giving the students the algorithm, which they probably would never remember, what would be the better way for them to learn this? Give them some measurements, have them measure it out, draw it out. Yes, give them a chance to play play with the concept, use pipe cleaners, use exploragons, use strips of exactly. So now we have the time for students to actually explore this concept, these concepts, and to see if they work and see why they don't work, see when it works and when it doesn't work. Comparing two triangles. This gives students the chance to compare and see, okay, what's alike? What's different? How do I know? Now, when it goes to applications of these concepts, you have modeling with perpendicular bisectors, whether it's an actual physical diagram or asking students to create a park and to place a water fountain at a certain location. Modeling with circumcenters, same thing, whether it's a roundabout and you want to know where do we place the center of this and the exit points. Modeling with centroids. Oops. So in all this, students have the chance to explore concretely. They have the chance to find using procedural skill and fluency, and then they have the opportunity to apply what they've learned. GeoStrips works well also. So looking at this next problem, uh-oh.
4 minutes, Janelle.
Okay.
3.
This is an activity where students are discovering a centroid, and this is in Solvis. This is chapter 5 in Solvis. And it gives students the opportunity to copy this triangle shown. Now, copying means they can use tracing paper or patty paper. If you wanted to give them a triangle of their own to use. And then it gives them an opportunity to use the ruler to verify the centroid is 2/3 the distance from each vertex to the midpoint of the opposite side. So you're going to have students measure their lines out, create medians and altitudes, label their parts, and then they're going to use a ruler to verify this information. So you're not going to give them the algorithm at first. They're going to explore this. They're going to create their own triangle. Once they do this, then you could introduce the concurrency of medians. You don't have to tell them what it is before they start exploring it. That's the point of exploration. And this is where you ask them, what do you notice? If you measure these parts, what do you see? What is common to all of our line segments? Then they could come up with okay, I have AG. Well, AG is 2/3 of AD, line segment AD. BG is equal to 2/3 of line segment BE. CG is equal to 2/3 of line segment CF. Oh, well, where is it that they meet in the middle? That is your centroid. Well, when do you see that? They can see it in artwork, and this would be a fun thing for students to do when they find it. Then you can show them how it is the balancing point. So like I said, you can have students explore this on their own. Either you could create it for them or you can have them create it, do the measurement so they can realize that no matter what size it is, once you find the centroid, that is the center and that's the balancing point. All right. Any questions? Yes, the centroid divides lines into 3 equal parts. As a reminder, this is for recertification credit. So on this last slide, we have 2 QR codes for you. So one QR code is our feedback survey for you to just give us some feedback, a formal reflection. that helps us determine what needs we met today and what needs we can touch base with you about at a later date, and a time to make sure we are supporting you as best as we can. The other QR code is your webinar attendance and the link. And Lorraine, can you put that link in the chat for me?
Yes,
This
I
is
will.
where you'll get your certificate. So this is the webinar attendance. And once you complete that, you are welcome to go. Have a great afternoon. Thank you so much for taking time out today to join us for this webinar.